Hi team. We've talked about the equilibrium constant KEQ for water, where we're looking at the concentrations of the products over the concentrations of the reactants. But let's think about KEQ for other compounds. We're going to start by thinking about weak acids because they're biologically very relevant. So they're going to be our focus for today. And rather than think of any particular acid, we're going to use the common shortcut HA. H, so we've got a proton to mess with, and A for acid. When this acid dissociates, it's going to form a proton and also a conjugate base. We'll call this the conjugate base, and over here we've got the acid. Now the way these are named, acids tend to end with ic, like malic acid or acetic acid, and conjugate bases tend to end with ate, like malate or acetate. As a biochemist, a question we might ask is if this acid, HA, is dissolved in the bloodstream or exposed in our body, is it going to dissociate to a proton plus the conjugate base? Or is it going to stay as HA? How will it affect the pH of our body? So we can use the equilibrium constant, or for acids, the dissociation constant, to answer that question. Similar to KEQ, the dissociation constant for weak acids is the concentration of the dissociated form, the proton plus the conjugate base, over the concentration of the complete acid itself. The larger Ka is, the stronger the acid is. And you can think about that because Ka and the proton concentration are directly related. The more protons here, the bigger Ka will be. So a larger Ka means a stronger acid, a more dissociated acid. So an acid that's more likely to be present as a proton plus conjugate base. The smaller the Ka, the weaker the acid, and biochemically these are more common. We're going to have a less dissociated acid, and it's going to be more likely to stay in the HA form. Let's look for a second at this table of acids with their Ka value. I'd like to try and identify the strongest and the weakest acid. And I think this will be our embedded question. The strongest acid, remember, is going to have the largest Ka. The weakest acid will have the smallest Ka. And just a reminder, if we put water on here, the Ka, or the KEQ for water, is going to be 1.8 times 10 to the minus 16. So we've thought about Ka, we've defined Ka here. Remember, this is the dissociation constant for an acid. But how does that relate to pH, which also has to do with protons in solution? Let's think about that. I'm going to rearrange this Ka equation to isolate this proton concentration variable. So let's divide both sides of the equation by protons, and we'll have to divide both sides of the equation by Ka as well. So why don't I do Ka on the bottom We've still got the conjugate base on the top, and then the concentration of the acid on the bottom. So I've just rearranged this equation to get this second equation here, and we can put a p in front of it. Let's take the negative log of each of these things. So we can do the log of 1 over the concentration of protons equal to the log of 1 over Ka, and plus the log of this concentration ratio, the conjugate base over the acid. Now, I don't really like what we've got happening right here because I don't want to call the log of 1 over H the pH. We've called the pH the negative log of the concentration of hydrogen ions. Well, in fact, 1 over this concentration is the same thing as saying the negative log. So let's rewrite this equation. The negative log of the hydrogen ion concentration is equal to the negative log of 1, nope, we're not 1 over anymore, of Ka. Plus, let's just keep this one the same, the log of A minus over HA. Okay, now we can rewrite it even further and say pH is equal to pKa plus the log of conjugate base concentration over conjugate acid. It's not the conjugate acid, it's just the original acid. So now we've got pH related to pKa. And remember, pKa is a derivatization of Ka. Guys, this is the dreaded Henderson-Hasselbalch equation. What are we going to do with this crazy equation? Well, the first thing I'd like to remind you of is that the log of 1 is 0. Okay, remember that. Let's make some sense of this Henderson-Hasselbalch equation. We don't even need to call it that because it's too confusing. I want to point out to you that the pKa, or this value for our dissociation constant for an acid, the pKa is equal to the pH of the solution when the concentration of acid and the concentration of conjugate base are equal to 1. When the conjugate base and the acid are present in the same amount, in equal amounts, this value becomes 0, and pH and pKa are the same. Let's say that one more time. The pKa of a weak acid can be defined as the pH of the solution when half of the original acid has dissociated into protons and the conjugate base. Let's look at this another way. pKa, as we just said, can be defined as the pH of the solution when half of the original acid has dissociated into protons plus the conjugate base. Let's look at this chart here. Along the left, we've got the pH of the solution, and in this case, it's a solution of acetic acid. And in order to induce this acid to dissociate, we're adding base or hydroxide molecules to the solution. So when we've added 50% of the hydroxide ions, you can see that the pH of the solution is just a little less than 5. So if we've added 50% of the OH, that means 50% of the acid has dissociated at this point. The pKa then is equal to the pH at this point. The pKa of acetic acid is 4.76. This point in the middle here is sometimes called the inflection point. And you can see it's noted that this point is where HA concentration is equal to A minus concentration. pKa is equal to the pH when half of the acid has been converted into the conjugate base so that their concentrations are equal. Now, let's consider the pH of the solution when it is less than the pKa value. If it's less than the pKa value, that is when pH is less than pKa, the solution is more acidic. HA, the acid, is more abundant. When the solution in question here has a pH that is greater than the pKa, well then the conjugate base is more abundant. So we're seeing that on the graph here as well. At a pH below the pKa value, we've got more of this original acid. And once the pH rises above the pKa value, the conjugate base is more abundant, more common in the solution. I want to remind you that the pH of blood and many other bodily fluids is around 7.4. So a lot of important biological acids will be dissociated at biological pH. That means they're usually referred to as the conjugate base, so it ends with an 8. Things like pyruvate or ascorbate or malate. Speaking of biological pH, our bodily pH is around 7.4, and a disturbance of 0.5 of a pH scale can lead to coma or death even. So we need to buffer or protect this bodily pH. And fortunately, acids and their conjugate base are really good at buffering or resisting pH change. And we can see that actually on our graph here. Let me clean that up. Remember, we're looking at the pH. We're measuring the pH of a solution as equivalents or portions of this strong base, OH minus, are added. And you can see that adding OH to this acetic acid, especially from here to here, doesn't really change the pH. So we're going from 0.1 to 0.9. That's from 10% to 90% OH. And yet we're only moving about 2 units on the pH scale here. Importantly, this weak acid, acetic acid, is best at buffering around its pKa, at a pH around its pKa. So the pKa is 4.76. It's best at buffering from about 3.76 to 5.76. Why is it that this buffering activity takes place? Well, if we've normally got our acid, which can freely dissociate into protons plus the conjugate base, but then we add OH to the system, now we're going to have the acid plus our strong base, and it will dissociate into the conjugate base plus a water molecule. We haven't affected the pH because we've sort of soaked up this OH molecule with the help of the proton. And any acid's ability to soak up that added base is going to be affected by the pH at which it's most able to lose or gain a proton. Let's consider this slightly more confusing graph of buffering by 3 different acids. On the bottom here, we've got acetic acid, which we just looked at. It's got a pKa of 4.76, so it's able to buffer down in this pH range. Next up, we can look at this phosphate solution. It's shown by the blue line here. You can see the pKa of phosphate is higher than that of acetic acid. And so if pKa 4.6 goes up to about 5.6, oh, look at this. Phosphate can take over buffering right about the same place that acetic acid is no longer able to buffer. So the middle of the pH range is buffered by phosphates. And up at the high end of the pH range, we've got ammonia. And you can see that this guy's pKa is 9.25. And it can cover a region of buffering just above what phosphate is able to buffer. So acetic acid, phosphate, and ammonia are great tools, chemical tools, to use in the lab to buffer a solution or a molecule or a reaction that needs to stay at a given pH. And once again, this is illustrating that near their pKa value, when the pKa is closest to the pH value, is where these acids are most able to gain or lose a hydrogen molecule to help buffer the pH of the larger solution. I want to mention that buffers aren't only important in the lab, they're also important in your body. We're going to discuss more, but you already know that when you metabolize sugar, you're going to produce ATP, but then also release CO2. And CO2, interestingly, dissolves in water. And when it dissolves in water, then we can see the formation of carbonic acid, which will naturally dissociate into a proton plus bicarbonate. And it's this system in the blood that can act as a buffer. For example, if we have a lot of acid in the blood, these protons will be soaked up, titrated away by HCO3, pushing back this arrow and producing more carbonic acid, which can then, which will be more abundant. Le Chatelier's principle tells us then that we're going to push this arrow in that direction. So we're going to be producing more CO2, which, we can just exhale that and produce water. So too much acid in the blood can actually essentially be exhaled as CO2. And of course, there's water. This is actually called compensatory respiratory alkalosis. That is compensating for acid in the blood through breathing, making your blood more alkaline or more basic. The very last thing I'd like to mention is the idea of polyprotic species. And we've only spoken about monoprotic so far. That is something that can dissociate into a single proton and a conjugate base. But polyprotic things can dissociate, can lose more than one proton. And so an example would be the amino acid glycine, and it's shown right here. And the first pKa, you can see we lose this proton right here. And then there's a second pKa value referring to us losing the third hydrogen up here. And we can see a titration curve that actually has two buffering points. So here's the first pKa when we lose the first hydrogen, and it buffers in solution around here. And then the second pKa where we lose this second hydrogen up here. Along the x-axis here, you can see we're going not from 0 to 1, but 0 to 1 all the way to 2 because we have two protons that can be used to buffer the pH. And this point right in the middle here, Pi, is the isoelectric point. And that refers to the point where the net charge, or rather the pH at which the net charge is 0. You can see in this central molecule here, it's not neutral. We've got a positive charge on one end and a negative charge on the other end of the molecule, but the net charge, the total charge of the molecule, is neutral at this isoelectric point between the two pKa's. All right, thanks for talking about pKa and buffers with me.